Welcome to this third webinar part of the ZHENIT E-learning program. We are here today with three speakers, who are going to talk about the future of waste heat recovery technologies. I'll leave the floor to Andrea, and let's start this webinar. If you have any questions during any time of the webinar, of course, feel free to use the chat and the Q&A section, and we'll answer them along the way. Okay, the floor is yours, Andrea.
Good afternoon again. A brief introduction from my side. My name is Andrea Frazzica. I'm a senior researcher at National Council of Research in Italy, especially located in southern Italy in Sicily. And today I will be presenting this first part of the webinar, which is about the survey of existing technologies for waste heat recovery on board of vessels. Then I will leave the floor to the other colleagues to go more in details about the technologies and modeling activities performed within the project. So the aim of this first part of the webinar is to more or less to set the overall conditions, the overall topic of the ZHENIT project. As you may know, ZHENIT is about improving the energy efficiency on board of vessels, mostly by focusing on the possibility of recovering waste heat on board of the vessel themselves. So why did we, apply for this project with this topic? Basically, looking at the current situation, as you can see here, let me switch. Okay, we have currently quite high emission intensity coming from large vessels, especially, and at the same time, in the projection, so the scenarios for the next years is that the billion of tons of these large vessels sailing around the world will be increasing. This is mostly due to, of course, good shipment, etc. But at the same time, the International Maritime Organization is setting very ambitious targets to reduce the emissions due to this shipping. So, of course, these are kind of contradictory scenarios, and it is also clear that if we look at the waste heat potential on board of vessels, if we consider very efficient propulsion engines like let's say a slow diesel engine, we have almost 50% of the energy contained in the fuels wasted, mostly because of poor conversion and of course waste heat generated at different temperature levels. So the target here is to try to recover at least part of this energy to increase the efficiency on board of vessels, so reduce other energy consumption on board of the vessel. To do so, first of all, I would like to draw your attention to this reference that you can see here and that you will see many slides. This is a paper that was prepared by part of the consortium of ZHENIT, which is a review about the waste heat potential and technologies on board of vessels. So many of the slides that I will be presenting today are, let's say, taken from this publication because it's a good, at least in my opinion, a good overview of what we can do to improve the vessels only recovering waste heat. So here it's exactly what we did at the beginning of the project. So to evaluate kind of an archetype of the onboard energy streams. Starting from the fuel, that of course is the main energy vector used of course to drive the vessel itself. So fuels is not used only for propulsion. That is of course the main target, but is also usually employed to generate electricity on board of the vessel, to kind of produce often steam at high and low pressure for different services on board of the vessels, also depending on the type of the vessel, as you can see here at the top, and also to generate cooling that is used for multiple applications that could be process cooling, but also cooling for people living on board, either the crew itself or the passengers in case of, for example, cruise ships or ferry ships. So we started from this archetype, and we then investigated how is it possible to increase the efficiency by recovering the waste heat that is always available on board. To do so, we at first performed an analysis of the potential of the waste heat on board. Basically, you can see here this graph on the left-hand side is reported by recovering both literature data and data coming from main engines manufacturers. And to estimate the potential of the waste heat here reported in megawatt thermal against basically the capacity of the engine. So of course, the higher the capacity at which the engine is working, the higher the waste heat availability. And of course, we have multiple sources of waste heat that can be recovered on board of the vessel, and this is mostly related to the temperature that we can withdraw from these waste heat streams. We identified three main sources of waste heat. Of course, lubricating oil, jacket water, so the cooling water of the engine, and then all the energy contained inside the exhausted gases, either from the scavenged air or the exhausted gas directly. Of course, if we increase the temperature in general, we also have more energy to recover. But what ZHENIT is trying to do is to recover as much as possible from the lower thermal capacity, thermal energy. Why is this the target? Because in the end, there are a lot of technologies already more or less commercial that are able to profit of high temperature waste streams, because of course the quality of the waste heat is much higher, and also from the thermodynamic point of view the conversion is much more efficient. While if you try to recover waste heat in the range, let's say around 100 degrees C, then of course you are recovering waste heat stream that is usually not very efficient in terms of thermodynamic conversion of the stream. So our target was to try to work in the range from 120 roughly down to 50 or so. That is purely waste heat at this stage. We moved then to analyze which are the possible waste heat technologies that can be, I mean, these are waste heat technologies that can be used, of course, also in standard stationary application. But we try to understand how much of these possible technologies can be also proposed on board of vessels. So whenever you have waste heat, you can basically convert it again to heat. So basically increasing or decreasing the temperature level or storing it. You can provide power, so heat to power, which is the most common application on board. And then, of course, you can drive cooling, heating to cooling processes, so to provide cooling on board. And in principle, you can also convert waste heat to mechanical energy. Some of these technologies are, as I mentioned already, at higher TRL, so higher technology readiness level, so closer to the market. Some others are still in the R&D level. And some of them, as you will see also in the next presentation, are actually part of the activities of the ZHENIT project. I will go through some of these technologies, just giving you some ideas of what we can do with waste heat, and yeah, to provide as much as possible in this short time an overview of the technologies. So for what concern heat to heat technology, so when we don't really convert it to another form of energy, but we try to make use of this heat for other applications. Of course, one of the applications is to store the heat on board in, let's say, sensible or latent storages to make use of this heat, for example, whenever the waste heat is not available anymore for producing hot water for people on board or for produce steam when possible. Some other technologies are different in the sense that they are directly converting it to another form of it. For example, using economizer that can be used for preheating water before generating steam. And of course, here you need the temperature ranges that are in the range from 120 up to 300. You can directly convert the waste heat in steam, so you can generate steam thanks to waste heat boilers. In this case, of course, you need much higher temperatures, usually coming from the flue gases. And then you can have other form of heat recovery, like recuperator that are basically waste heat to air heat exchangers, regenerator that are used to again preheat air inside the process. And you can also generate steam at different pressure levels for different applications on board. Of course, all these applications are characterized by a quite mature level of development, but at the same time, usually they are, let's say, they can suffer of different drawbacks, like the need of very bulky systems, also the possibility of suffering of fouling issues, especially when you try to make use directly of flue gases. But in general, all these applications are extremely effective when you try to exploit quite high temperature levels from the waste heat. One of the most advanced solutions on board, in case you want to generate power out of it, is the defined combined steam and power turbine. A combined steam and power turbine is a technology that is able to extract the energy, so the waste heat both from flue gases to drive a gas turbine, and then in cascade to generate steam, and with the steam turbine again provide power. In this way, you have basically, as you can see from this picture, a power turbine and the steam turbine on the same generation line, and you can maximize the exploitation of the waste heat capability to provide electricity. So as you can see, in this case, some of the most relevant, I would say, companies working in the maritime sector, especially for engine and power generation board, already developed products that are basically on the market. And as you can see, of course, the efficiency of the process is highly dependent on the engine load. So the higher the engine load, the higher the efficiency that we can achieve because of the higher waste heat availability. But in general, all these technologies are working in the range between 8 and 12% of maximum efficiency, which means the electricity generator divided by the waste heat used. A different technology that is still used for providing power, and that is also part of the activity of the ZHENIT project, as it will be, let's say, presented later on, is the so-called organic Rankine cycles. In this case, we are working again with a power generation cycle, but instead of using steam as a working fluid, we usually switch to different working fluids that are usually organic fluids that are able to profit of lower waste heat temperature to run the power cycle. Here I'm not going in the details, but as you can see, a lot of investigations were performed. To be honest, most of them are still in the numerical investigation phase to analyze different working fluids. Most of them, as you can easily understand, are fluids that are, let's say, derived from the heat pump technology that are now also used for power generation. And as you will be probably hear from our colleagues from NTUA, this was also part of the ZHENIT project to select the proper working fluid for the proper operation of VRC, especially when you want to exploit extremely low waste heat streams like around 100 degrees C. I have to say that some of these technologies are already on the market by some European companies and are in other projects in which we were also involved, have been also installed on board of vessels to evaluate the achievable performance. A different application is the one where we try to convert waste heat in cooling provision. In this case, basically there are two different technologies. The most, let's say, advanced one in terms of maturity is the absorption cooling technology. In this case, basically the waste heat is used to drive a solution that is usually made out of lithium bromide water or ammonia water. And basically the process is like a standard heat pump, but we are driving the process out of waste heat instead of electricity, instead of mechanical energy used for compression. And the positive feature here is that you can operate the system under different configurations. So the so-called single stage, in which you have a single absorber, so a single compressor, let's say, but you can use here different working fluids, and you can go down to minus 30 even degrees C to provide cooling on board. But you can also work with different integration, so having cascading systems in which you can increase the overall efficiency of the system, and you can even achieve much lower cooling temperature, up to the hybrid solution, in which you integrate the absorption chiller with the compression chiller to extend the operation of the system, still keeping very high thermal efficiency. As you can see here on this table, the COP here is reported as a thermal COP, so the ratio between the cooling, the energy provided for cooling divided by the energy provided as a waste heat. So as you can see, this is usually below 1, but still, let's say, quite interesting for the application. The other option is the adsorption one. In this case, we are not using a solution, we are using solid sorbent material. The overall principle is the same, but the difference is that we are using a fixed heat exchanger containing this adsorbent material that is acting as a thermochemical compressor. So the overall working cycle is exactly the same, but in the end, we can use extremely low GWP refrigerant, or let's say virtually zero GWP like water. And the main feature here is that you can make use of this process, as you can see from this picture, also to desalinate the water. Because if you let salted water entering the evaporator of your machine, once you run the process, you can discharge on the condenser side a certain amount of water that is desalinated, completely desalinated. And at the same time, on the evaporator side, you can also provide the cooling capacity that is needed for the process. So in the end, it's a system that gives you the possibility to have a dual operation of your technology. At the same time, compared to the absorption one, the adsorption chiller and desalination system is still, is on the market, especially the cooling technology, but not fully deployed as for the absorption one. There are still some challenges to face, and this is also part of the investigation performed within the ZHENIT project. So to conclude, I'm here reporting a table that is summarizing at least all the technologies that we were investigating in this review paper that I mentioned at the beginning of the presentation. As you can see, there are multiple technologies already on the market or still at the R&D stage that are under let's say that gives us the possibility to exploit waste heat on board of the vessels. I have to say that some challenges that we identified are related to the size in terms of volume and also bulkiness of the solution, because of course this is one of the most critical parameters to be able to shift a technology that is at least conceived at the beginning as for stationary application on a vessel because of the space constraints, but also of the weight that can reduce the overall efficiency of the sailing. Again, I will suggest you, if possible, to have a look at this paper. For sure, you will find a lot of interesting information, and of course, I'm happy to answer any doubt or question out of this presentation. Thank you.
Thank you, Andrea, very much for your presentation. I'll leave the floor now to Joseba.
Thank you. Yes. Okay. So thank you, Andrea. Okay. Can you see my presentation?
Yes, we can.
Okay. So after this first block, we are going to continue with the main feature of some of these technologies that we are developing in ZHENIT Project. Okay. So the technologies we are going to explain today will be the suction desalination and cooling unit that is developed by ZNR. Then the isobaric expansion engine that we are developing here in Aspatia. And the last one, the ORC ejector integrated heat pump led by NTUA in Athens. Okay. So as an expert in the respective technologies, Andrea and Kostas, they are going to join in my presentation in order to explain correctly their technologies. Okay. So I give you the floor to continue, Andrea. Okay. So go ahead, and now it's your turn. Okay. Why it doesn't work? Sorry.
Thank you,
Yeah.
Joseba. So I'm back for this part of the presentation. So as already briefly mentioned during my previous presentation, within the ZHENIT project, we are working on the development and testing of absorption, desalination, and cooling unit. So as mentioned before, absorption technology is basically from the thermodynamic point of view, exactly like a heat pump or a chiller. So it's characterized by an evaporator and condenser and a compressor. The compressor in this case is not a mechanical compressor, but is a thermochemical compressor, which means that it exploits the characteristic of some materials that are porous materials to basically pressurize the working fluid from the evaporator to the condenser, just exploiting the waste heat. Within the project, specifically together with CNR, so my institution, together with the Absorption Technologies, which is an SME from Germany, are developing a prototype of absorption chiller and desalination unit for application on board of vessels. So the main feature of this prototype are reported here in this schematic. So I have to say that absorption chiller technology exists since many years, and there were in the past, especially some companies also in Europe manufacturing and selling this technology, but they were based on a kind of different approach. Absorption Technologies patented a new solution to try to improve the efficiency, but especially reduce the capital cost of the technology. And basically, they are trying to integrate all the process inside the reactor that is here reported as with the number 1, these 2 absorption modules. We need 2 absorption modules because the system is working kind of in a bulk operation. So when one of these absorption module is pressurizing the fluid, the other one is absorbing, so it's generating cooling capacity. So we need to have two absorption modules to have a continuous cooling provision. The main difference is that in this case, we have the evaporator and condenser that are basically inside the adsorption module itself. So the process is fully active inside that vessel. And then we have the refrigerant, that is water, that is transferred inside the process through a pump, through a centrifugal pump. In this way, we have a distribution in the liquid phase. So the water, of course, in the liquid phase is much denser than the vapor phase, and also the cost is reduced because of the size of valves, etc. You can switch to the next slide. Yeah. And this is kind of the simplified P&ID of the system. So basically, we have these two rectangles in the middle that are the two adsorbers working in counter phase. The process is driven by the waste heat coming from this hot source on top of the picture, while at the bottom we have these two tanks, the blue and yellow one, that are containing the salted water and the fresh water respectively. So what happens is that when we start the adsorption process, the salted water is sent to the adsorber. It evaporates inside the adsorber, and so of course the salt remains on the evaporator side, while the fresh water is shifted to the condenser side. And then when we regenerate the material, the water contained inside the material is condensed, and then we extract on the condenser side the fresh water, so the desalinated water. As you can see, the water here is facing basically two evaporation and condensation steps. So at first it evaporates from the evaporator and it is absorbed by the material. In the following step is desorbed by the material and condensed. So it's like, I can tell you it's extremely desalinated water, the one that we can extract from the tank, from the condenser tank. And at the same time, of course, since we are evaporating water, we are also generating cooling. So in the end, this system is able to provide both cooling the capacity to the user, but also a certain amount of desalinated water. So if we move to the next. Yeah, within the project, we are having two phases of experimental testing of this prototype. The first one was completed by Sorption Technologies in their facility in Germany, which was just a pre-commissioning. So they realized the prototype and they tested it in order to validate the main operating conditions. Now the prototype is shifted to CNR and it's currently under testing. I will provide you just a few ideas of the preliminary results we got so far. If you can go ahead, Joseba. Yeah, these are the conditions we tested so far. So as you can see, we are driving the process at 85 degrees C, which is more or less the temperature that we can expect as waste heat on board of the vessel. We are providing cooling at 15 degrees C, so basically for distribution with fan coils on board. And we are rejecting it to the ambient at 30 degrees C or 35. These are extremely high temperatures. If you consider that in principle on board of vessel, we can even make use of seawater to condensate the process, but we wanted to test the prototype at very high condensation temperature because, of course, it may happen that for any reason you need to make use of a different recooling system like a dry cooler. And we also changed some conditions like the driving temperature down to 75 degrees C in case, for example, of less effective waste heat recovery on board. If you go ahead. Yeah, this is the typical evolution of a working cycle of the adsorption chiller. So you can see on the top all the temperatures that are measured inside the prototype. And as I mentioned, it is not completely steady state operation, the one of an adsorption chiller, because you can see that every process is characterized by kind of an exponential curve. This is due to the fact that the adsorbent material is getting saturated along the working cycle. So whenever the material is saturated, you need to switch to the next phase. And at the bottom, you can see, I mean, I'm not going into the details, but basically you can see a bit more focus on the medium temperature, so the heat rejection temperature to the ambient. You can see that we are, in this case, providing inlet temperature around 30 degrees C, while the exit temperature is around 34 to 35 degrees C. This is basically the heat rejection to the ambient. While on the bottom right, you see the cooling side. So in this case, we are entering around 15 degrees C. This is the purple line here, and we are providing cooling down to 10 degrees C. So we are able to generate a temperature difference of around 3 to 4 Kelvin, which is the cooling effect useful for the end user. So if you switch to my last slide, Joseba. Yeah, this is just a very quick summary of what we got so far. The testing are currently ongoing. We completed a characterization using 90 degrees C as a driving temperature, and then varying the temperature difference between the heat rejection and the cooling temperature. So, which is this on the x-axis is the delta T between MT, so medium temperature, and LT, which is low temperature. As you can see, under these conditions, we can achieve, let's say, a cooling capacity up to 7 Kelvin more or less. 7 kilowatts, with a thermal COP that can be around 0.42. This is, of course, happening when we have roughly 12 degrees C of difference between the medium and low temperature. Since our nominal condition is 15 Kelvin of difference, under these conditions, we are able to generate roughly 5.5 kilowatt with the thermal COP above 0.3. We are now testing this system with different driving temperatures, and the final phase will be testing the same prototype to generate at the same time both cooling and desalinated water. This will be the last outcome of our investigation before going ahead with the full integration on board of the vessel. Thank you for your attention, and again, I will be happy to answer any doubts or questions.
Okay, Andrea, I will continue with the next technology, okay? Following the isobaric expansion engine, the isobaric expansion engine is a thermodynamical cycle that generates a mechanical work, okay? And for that, utilize temperature difference between a hot source, that the hot source comes from the low-grade waste heat that we reach from the ship's engines, and then the cold source that in this case we can use, for example, the seawater, okay? So taking into account this temperature difference and the pumping that we apply to the refrigerant, and then the expansion that this refrigerant suffer, this prototype is able to generate mechanical work, okay? About the prototype, the main components we can see in this image in the left side, we can see 4 heat exchangers that are the evaporator, the condenser, the subcooler, and the regenerator. Then we have the feed pump, the isobaric expander, that is the main component, and also the oil power pack that I'm going to explain in the next slide, okay? About the simplified P&ID, okay? Here I try to explain you correctly how it works this prototype, okay? So as you can see in green lines, you can see the refrigerant circuit, and then with yellow lines you can see the hydraulic module, that is the circuit responsible to give us the work output or the hydraulic power in this case, okay? So starting with the feed pump, instead of have an electrical pump to move this refrigerant, we use a cylinder piston system that is moved by a oil power pack, that is an hydraulic pump. This hydraulic pump moves the oil that is responsible to move these pistons that are two single acting pistons that are in the same in the same shaft, and in the middle of this shaft, they share a double-acting piston that is responsible to pump and to increase the pressure in refrigerant. So with this motion in the feed pump, the refrigerant, as I mentioned, is pumped and increases the pressure and comes to the regenerator. In the regenerator, increase its temperature and arrives to the evaporator where the refrigerant after that is in gas state. Then in high pressure gas refrigerant, when enters to the isobaric expander, is the responsible to move this isobaric expander that is mainly the same geometry than the feed pump. Are two external single-acting pistons that share in the shaft a double-acting piston in the middle. So in this expansion process, the refrigerant is able to move the piston and in the same time to increase the pressure of the oil, that is the oil that are giving us the work output. So after that, when the refrigerant is expanded in low pressures, the refrigerant arrives to the regenerator. Here decrease its temperature, arrives to the condenser and pass to liquid state. And lastly, we have the subcooler. The subcooler is responsible to decrease the temperature of the liquid refrigerant, and it's very important because it's the main responsible to prevent the cavitation in the feed pump. Okay, because if the refrigerant is colder, it's easier to prevent this phenomenon. Okay. Apart from that, if we focus in the hydraulic module, in the work output, here we have two main components that are the accumulators. Okay, we have the high and low, in the high and in the low lines, we have two accumulators. The high line is the responsible to guarantee us the flow stability. Okay, for that we use a bladder accumulator, and is pressurized by nitrogen. So it's very important to define correctly the nitrogen charge, and due to that we guarantee a correct flow stability. And apart from that, in the low line also we have another accumulator that is the responsible to give us enough low pressure to guarantee us also that we don't have any cavitation phenomena in this part of the circuit. Okay. Apart from that, as you can see, we have a needle valve that is the responsible to throttling the circuit. I mean, to generate this different pressure that we want to generate in the oil circuit. I mean, it's an obstacle that the oil have to pass, and due to that, the result is that generate a pressure difference. Okay. Apart from that, we have a flow meter in order to know all these variables that we need to know to calculate the hydraulic power, okay, and other components. And in the right side of the slide, you can see nowadays how looks our prototype in Aspetia's lab. Okay. Okay. Next slide. 1 second. Okay. About the facilities in our laboratory in Aspetia. Currently, we can generate more or less in 300 thermal kilowatts in Tecnalia's labs. Okay, and then this heat is moved by 3 water lines or water rings. Okay, that are separated in 3 levels: high temperature ring, medium temperature ring, and low temperature ring. Okay. And then for this ZHENIT project, we installed different substations in which, and in these substations, the idea is to connect all these prototypes that we are going to bring here to Aspetia. Okay. This example, for example, is for isobaric engine and association machine prototypes. Okay. And as you can see here, this substation is going to give us the possibility to test two different prototypes using only 2 lines, the medium and the low temperature rings. Then these substations have in their equipment water pumps, temperature transductors, flow meters, and I mean this is the this is the idea we have. For the moment, you are going to bring here your prototypes. The idea is to have this autonomy to decide how much heat you want to bring to your prototype. In our case, for example, we define our flow rates and our temperatures, and the idea is to define all the rest of the temperatures and flow rates to carry it out correctly with all this equipment. And this is how currently looks these substations in our laboratory. Okay. So following with the testing matrix, we have 4 variables when we decided to start with these testings. 2 of them are the supply temperatures of the water in the condenser and in the evaporator that we decided to define in this way. I mean, we have the fresh water in 20, 30, and 40 degrees, and the heat source or lower heat source is in 80 and 90 degrees. Okay. Apart from that, we decided to put all time the feed pump frequency in 30% of frequency. This frequency is the velocity we are giving to the motor that supply the oil power pack that in the same time supplies the feed pump. Okay. And lastly, we have the valve that give us this pressure difference. Okay. For that, we do to define first of all the maximum pressure that we can reach in each conditions. I mean, if we are talking about, for example, water 20, water 80, we throttle the maximum we can the valve, and if we see, for example, here, for example, if we go to the result, I can explain better. If we go to the result here, okay. For example, here see that water 20, water 80, we were able to generate 43 bars. So this is the maximum pressure that we can generate in oil in this condition. Okay, and then the idea is to test other 2 conditions, one medium one and a minimum one. For example, in this case, currently we don't do these tests, but the idea is are planned to be done during these weeks. Okay, and the main results that I want to highlight here are that, first of all, as you can see, that the maximum value we reached was in condition water 20, water 90, that the hydraulic power we reached was 289 watts and 3.10% of efficiency, and the minimum value we reached was in water 40, water 80, with the value of power in 128 watts and 148% of efficiency. Okay. As you see here, apart from the conditions that are expected to be done, we also tested water 35, water 90 condition. Why? When we started testing with 40 degrees of water supply in condenser, we realized that the feed pumps did strange things. For example, strange noises, and we don't like these noises, so decided finally to be conservative and says, okay, the feed pump doesn't feel very comfortable in these conditions, and maybe it's better to not force anything and test in better conditions. So due to that, we take extra points, in this case water 35, water 90, and in these conditions we didn't hear any noise or anything. And apart from that, yes, the other conclusion finally that we take were, first of all, the hydraulic accumulator. As I mentioned, in a work output hydraulic module, we have an hydraulic accumulator in the high pressure line, sorry. And this hydraulic accumulator, we see that is very important and has very positive impact in flow stability. If the charge of nitrogen is not the correct one. I mean, if we are with a low pressure in nitrogen or in high pressure in nitrogen, the accumulator it doesn't have a capacity to guarantee us a stable flow. So was difficult to define the correct nitrogen pressure, but finally we reached it, and a conclusion is that it's a very positive impact. Apart from that, we see that if the temperature difference between the sources, I mean between the hot source and the heat source, is bigger, the power we are reaching and the efficiency we are reaching are better. Apart from that, we see that if the valve is too open, I mean if it's too free, I mean, yes, because it's reaching a lower difference of pressure, the power reduced significantly. So it's better to generate more pressure differential and less flow rate than vice versa. Apart from that, suction pressure in feed pad, as I mentioned, could be critical because, as I mentioned, as bigger, higher suction pressure we had, started the noises and all the preoccupation. So finally, we decided to decrease these pressures using lower supply temperatures in the condenser. And the last conclusion we obtained was that if we change the cold source temperature instead of hot source temperature, the changes is bigger. I mean, it's more sensitive, the prototype, if we change the cold source than if we change the hot source. And yes, these are the conclusions. And lastly, I want to mention our next steps that are, first of all, to fulfill all these conditions that in the table you see empty. And the next step also is to optimize the feed pump frequencies. All these tests we did in constant frequency of 30%, and now the idea is to carry out in different frequencies and find the optimal one. Okay, so that's all for the isobaric expansion engine. Now I give you the floor, Kostas, to continue with the RC ejector. Okay.
Thank you very much. Okay. So let me begin with the ORC ejector integrated heat pump. So basically, this is a rather complicated prototype, and its main purpose is to utilize, of course, waste heat and produce. Sorry. Okay. To produce electricity, heating, and cooling. And basically, this prototype is based on 3 different conceptual technologies. The first one is the organic Rankine cycle, which is a standard technology for low temperature heat recovery and power generation. And this is used in our prototype for the production of electricity and for combined heat and power production. Then we have a second technology that's part of this prototype. This technology is the ejector cooling cycle, or denoted ECC in this presentation. And basically, the ejector cooling cycle is a thermally activated cycle. It's very similar to the standard vapor compression cycle. The only difference is that instead of a mechanical compressor, we have an ejector device, and the purpose of this ejector device is to utilize high pressure, high temperature flow that is generated with waste heat to entrain low pressure vapor that leaves the cooling evaporator of the system. And what has been implemented in our prototype is a variation of the ejector cooling cycle that also combines a vapor compression cycle. So we have basically a hybrid, thermally activated and mechanically driven chiller that is called ejector vapor compression cycle, or EVCC, according to the terminology that we use. So in total, we have 4 different operating modes because of all these technologies that are coupled together. First of all, we have the electricity generation mode. In this case, we only generate electricity. And what we have is a standard ORC with a recuperator. The recuperator is basically a heat exchanger that is used for recovering part of the heat of the expanded low pressure vapor to preheat the liquid organic refrigerant before it enters the ORC evaporator. So in this way, we can achieve an improved thermal efficiency for our system. Then we have a second operating mode. Basically, this is the CHP mode, combined heat and power mode. Again, we have the ORC. But what happens in this case is that we don't use the recuperator because we prefer to utilize this, the heat of the expanded vapor to produce useful thermal energy. And then we have another operating mode that is combined electricity and cooling generation. So this is CCP mode. And what happens in this case is that we have the operation of the ORC, and at the same time, we also operate the ejector vapor compression cooling cycle. So as you can see on this diagram here, after the ORC evaporator ECC generator, this is 0.5, we have the option to split the flow and use one part of the flow and send it to the expander of the ORC to produce electricity. And we can use some other part of the flow and send it to the ejector to entrain low pressure vapor at 0.9 leaving from the cooling evaporator. And at the same time, we have the option to use these compressors that you see on this layout. And I will come back to this point later. And in this case, as I said, we have electricity produced from the expander and cooling at the same time. And finally, we have a cooling only mode. In this case, we can use either the ejector vapor compression cooling cycle, the EVCC, or the ECC, or the standard vapor compression chiller mode. So what I was saying previously is that in this implementation here, we have also some compressors in addition to the ejector. And there are many ways in which these two components can be coupled. The first way is to have in parallel the compressor and the ejector. So in this case, the flow leaving at 0.9 after the cooling evaporator is split into two parallel streams. And the first one is compressed by the compressor, by the mechanical compressor. So we have a standard vapor compression cycle. And a second part of this flow is sent to the ejector. So the ejector cooling cycle and the compressor operate in parallel. And we have another way to couple these two devices. The second way is to have a serial coupling. So in this case, what happens is that we have the vapor leaving at 0.9, and this vapor is sent first to the compressor, and then after leaving the compressor, it is applied to the ejector. So the compressor and ejector are connected in series, and the advantage here is that the compressor operates at a smaller pressure ratio, so the COP of the vapor compression cycle is improved, and also the ejector performance is also improved because it entrains vapor at a somewhat higher pressure, so it has an easier capability of entraining more flow and increasing the cooling output of the whole system. So in addition to these components, you can see that we have also the condenser where heat is rejected or recovered as useful thermal energy in CHP mode. And we also have the subcooler. This is similar to what was mentioned previously about the isobaric expansion engine. So the subcooler is not a necessary component. I mean a thermodynamically necessary component, but its purpose is to prevent the cavitation issues in our pump, which is used for pressurizing the working fluid. So next slide, please. So here you can see a PNID diagram of the concept that I showed you previously. Of course, the actual system is somewhat more complicated than the conceptual one. Some differences that you can see here is that we have not one, but two expanders. These are the expanders. I don't know if they're very clearly visible. The reason for using two expanders is basically what we do in this test rig is that we use commercial off-the-shelf components for everything. So we used some Sanden scroll compressor models, and these are modified and operated in reverse. So they are converted into expanders. And because these expanders have these compressors that are used as expanders in our test rig have very special characteristics, in order to enable their use under the conditions of our test rig, we had to use two of them in parallel. And something similar happens with the two compressors. You can see that we have two compressors in the vapor compression cycle, And again, we have to use two compressors and not just one. And you can see that we have a series of valves, and these valves basically are used for changing between all these different operating modes that I mentioned previously. And regarding the EVCC mode, these valves enable us to have the ejector and compressors either in parallel or in series. And we have the ejector device. This ejector device, it's worthwhile to note that this is not a commercial component. This was designed in our lab. We had, for its design, we used some 1D simulation models that are rather simplified. And then we fine-tuned the geometry based on CFD analysis that we carried out for this device. And on the right-hand picture, you can see a photograph of the whole prototype as it was developed, and it is currently located in NTUA. So you can see that it has it takes up a lot of space. In reality, it is not necessary. It could have been much more compact. The reason for this is that we decided to follow a very conservative approach because we were not sure what problems we would face during the experimental testing. So we had to allow enough space between all the components to do modifications if needed or any other work. So in reality, this system could have been much more compact. So can we go to the next slide? Okay, so after developing this prototype, we have been carrying out an experimental campaign in NTUA, and this experimental campaign involves a full characterization of the prototype, first of all, under variable conditions, and secondly, its full automation. So the goal is to end up with a fully automated prototype that can very easily change between different operating modes, and this is one of the main challenges that we are focused right now. So to do this experimental testing, we use the infrastructure of our laboratory. This infrastructure involves basically a natural gas boiler that is used for producing hot water. And the maximum temperature of the hot water is about 80-90 degrees Celsius. And this is used as a heat source for the prototype. And the infrastructure also includes a chiller, and the chiller is used for producing water at very low temperatures. So at a very low temperature level at 5 to 10 degrees Celsius to emulate chilled water, to emulate, for instance, cooling demand. And we can also produce water at ambient conditions, emulating seawater, which is basically the heat sink of our system. So we have all these three temperature levels, hot, medium temperature, and low temperature, that are generated with a lab infrastructure, and this is used for our testing. Can we go to the next slide? So here is some testing, some of the first results that we have gathered. In the recent months, we have a lot more results, but these are the first ones that were collected in the first testing campaign. You can see here a table with various operating conditions that we tested the prototype. Basically, you can see that the maximum operating temperature was up to 82 degrees Celsius. So basically, the prototype was designed for a higher temperature to operate at a maximum temperature of 140 degrees. But testing in NTUA lab was limited to a low temperature because our infrastructure does not allow to go at higher temperatures. So this means that the results that we have collected are a bit underestimate the actual performance of the system. So under real testing conditions, we would be able to have better results. And you can see some other temperature levels. Basically, I think the most important ones are to mention that the cooling the chilled water temperature at the evaporator inlet was ranged between 8 to 14 degrees. And we have some results on these diagrams. So these three results in the top left diagram, you can see some results that are related to the electricity only mode. So in this case, we just have the ORC with a recuperator. And the tests refer to cooling water temperatures at the condenser of the system between 15 to 40 degrees. Under these conditions, we have a maximum pressure of the ORC at 5.85 bars. And we know from theory, and this was also verified from the experiments, that increasing the cooling water temperature led to a reduction of the thermal efficiency. Overall, the thermal efficiency ranged to a maximum, from a maximum of about 3% at the lowest temperature to about 1% when we raise the temperature to 35 to 40 degrees. And you can see here that the experimental testing also involved some optimization of the expander, of the rotational speed of the scroll expanders that we use. So it was identified from these experiments that the best performance was obtained at about 2000 RPM compared to the other rotational speeds. And then we have the top right diagram, and here you can see a comparison of the performance of the ORC with and without the recuperator. So again, we have this similar variation pattern of the efficiency with regard to the cooling water temperature or the condenser pressure. What is interesting here to point out is that in our prototype, we had better performance when not using the recuperator. So this may seem paradoxical from a thermodynamic point of view. The reason for this is that the recuperator had very high pressure losses, which essentially led to a significant reduction of the efficiency of the system. So under our conditions, it was proven that the recuperator does not provide any electricity performance benefits, electricity efficiency benefits. And on the bottom diagram, you can see some experimental results that are related to the operation of the ORC and the ejector cooling cycle at the same time. So here we have, you can see time, a temporal evolution of the electricity generation and the cooling power that is produced from the system. And you can see that we have some variations, and these variations are basically because of the fact that when we switch from ORC only mode to parallel mode in which the ORC and the ejector also operates, we need to do some adjustment of the rotational speed of the expanders to stabilize the pressure, the maximum pressure of the system. But based on our results, it was possible to stabilize it. And you can see here that we had the power output ranging to about 900 watts, and the maximum cooling power was about 1.2 kilowatts. And I need to mention here that the thermal input to the system under these experiments was about 30 kilowatts. So this is basically an overview of the results that we got. It is important to highlight again that these experiments were carried out under a very low, under a lower temperature than the temperature for which the system is designed. So these are not representative of the actual, let's say, performance. However, the plan is to utilize these experimental results and validate models that we have, and then be able to extrapolate on the performance of the system at higher temperatures. Next slide, please. So to conclude, this experimental campaign was able to demonstrate the successful operation of the ORC that we designed for both operating modes, electricity and CHP. And this is globally the first instance of the successful experimental demonstration of the concept of the parallel organic Rankine cycle and ejector cooling cycle for combined cooling and power. And it was also the globally first demonstration of the EVCC concept, in which, I remind you, the ejector was coupled with a vapor compression, with compressors, to have this hybrid electricity and heat and thermally activated cooling. And the future steps now of this work is, as I said in the beginning, it's very, very challenging to be able to have a fully automated prototype, but we have almost finalized this at this period. And the next steps in experimental testing will involve this fully automated operation to showcase that it is possible to have stable operation and effectively change between different operating modes. Because this is one of the main, let's say, advantages of the system, that it is very flexible and it is important for us to be able to achieve this goal. So this is it for the ejector integrated heat pump. Of course, I will be happy to answer any questions. The topic of this presentation is modeling aspects of the ZHENIT technologies. In this project, we are responsible for developing a dynamic modeling platform, and the purpose of this platform is to be able to carry out dynamic simulations of all the ZHENIT technologies to be able to evaluate their capabilities in terms of efficiency increase and energy savings. So this slide shows a general overview of this modeling platform that we are developing. Basically, the inputs of this platform is the engine load or waste heat profile of the vessel, the seawater temperature profile with regard to time, also the heating cooling demand of the vessel, and also the various sizing, let's say, parameters of the ZHENIT technologies. And the main outputs are the electricity generation, the cooling production, and the heating production profile that is achieved during a whole, let's say, time frame of operation of the technologies. And then this enables further calculations, for example, to calculate the fuel savings and the economic savings and emissions reduction. So, for example, you can see here that what we get as an input, that we feed as an input to this platform is, for example, the engine load profiles and the heating demands and the cooling demands of the vessel and the seawater temperatures throughout this trip. And I remind you now that in this platform we incorporate 4 ZHENIT technologies. So we have 3 active ZHENIT technologies, and these include the isobaric expansion engine and the sorption desalination chiller and the ORC ejector integrated heat pump that were presented in the previous presentations. And then we have one passive technology, which is the latent thermal energy storage system. So each technology has a specific particular temperature operating range. So it is important to highlight that the isobaric engine and the sorption desalination chiller operate with lower waste heat temperatures from 60 to about 90 degrees Celsius, but the ORC operates at a higher temperature that can reach up to 140 degrees. And then we have the latent thermal energy storage, which is in principle a more flexible technology because we have different PCM materials, and depending on the desired temperature level, we can select the appropriate material. To set up the modeling platform, the activity was based on a generic layout of all the ZHENIT technologies. This generic layout was devised by CNR in the project, and this is basically a very general, let's say, scheme of how to interconnect all of these technologies that I mentioned together. So, as I said, we have the ZHENIT technologies, the active ZHENIT technologies that work under 2 distinct temperature levels, a higher temperature level above 100 degrees and lower temperature level below 100 degrees. And then we have the ORC operating at high temperatures, and the other 2 technologies, the sorption desalination chiller and isobaric engine, working at up to 90 degrees. So considering this scheme, and because these technologies have these distinctions between regarding the operating temperature ranges, we first set up this conceptual design of the dynamic modeling platform. So in this case, we have the vessel engine, and from the vessel engine we have 2 sources of waste heat. We have the exhaust gases that are at high temperature, and these are coupled with a high temperature thermal energy storage system. And then we have the ORC, because, as I said, this technology operates at higher temperature. And then we have the jacket cooling water of the vessel engine, and this is coupled with a low temperature thermal energy storage system. And then we have basically the option to couple this with the sorption desalination chiller, the isobaric engine, and the heating demand, which can be done. In this case, we have heating that is directly utilized for covering the heating demands of the vessel. And this is basically a more, let's let's say, sophisticated description of what I described you. So we have the vessel engine and we have these streams of waste heat. And we have, in the first case, in the case of the ORC of the high temperature system, we have a heat transfer oil that is used at high temperature, and we have a buffer tank, and then we have the latent thermal energy storage system, and then we have the ORC system. And in the other case, we have the jacket cooling water, then we have another circuit of hot water that is at lower temperature, and then we have accordingly the low temperature thermal energy storage, and then we can have the isobaric engine and the solvent desalination chiller, because these two operate at similar conditions, they are coupled in parallel in this scheme. So in all of these cases, we have this generic, let's say, concept in which we have the waste heat stream, be it exhaust gases or jacket cooling water. We have a waste heat recovery heat exchanger, and then we enter the heat transfer loop. In this case, we have the heat transfer fluid, we have a circulating pump, and then we have the buffer tank. This is a pressurized tank that acts as a buffer, basically. Its role is not to do thermal energy storage, but more to stabilize the system. And then we have the thermal energy storage, the latent thermal energy storage. We have a circulating pump, and then we have a valve, and valve V1 and V2. And basically the role of these valves is to regulate the operation of the system and switch between different operating modes. And I will come back to this point later. And in the end, we have the active ZHENIT technology. So this block here can be either the ORC, the solvent desalination chiller, or the isobaric engine. And what we do is that we use some surrogate models, some performance maps of the active ZHENIT technologies, and these are provided as equations, as polynomial equations in this block here. So the first step of the modeling activities is to come up with a detailed sizing methodology under which we can define all the specifications of the components before we can proceed with the dynamic simulations. So the first component to define is the waste heat recovery heat exchanger. This is this heat exchanger here. So for example, we have some specifications for this heat exchanger. We have, in this case, we can have, for example, the exhaust gases, and we have this temperature profile of exhaust gases. And what we do is that we can assume a minimum exhaust gas temperature that is compatible with the chemical properties of the exhaust gases. And then we have several degrees of freedom regarding how to size the thermal oil or the heat recovery fluid, for example, the heat transfer oil that goes into this heat exchanger. And in our simulations, we have considered that based on data that we have from vessels, we have, in the case of the exhaust gases waste heat recovery, we have a very large heat duty of about 1 megawatt, and we have 250 kilowatts for the low temperature waste heat recovery heat exchanger from jacket cooling water. And these are some temperature ranges. For example, in the exhaust gases, we have a maximum temperature of the oil that is about 190 degrees, and the oil lives at 140 degrees. And in the case of the jacket cooling water, we have lower temperatures that are between 70 and 80 degrees. So after determining all these conditions that correspond to the nominal point, what we do is we size this heat exchanger and we estimate its area. The second parameter that needs to be sized is, of course, the size of the ZHENIT technologies. So, for example, after coming up with a nominal heat duty of the waste heat recovery heat exchanger, we need to specify what will be the size of the active ZHENIT technologies. And here we use basically a factor that is called F technology in our models. And this is a normalized parameter that shows the size of this technology compared to the size of this heat exchanger. This allows us to have some normalized results that can be easily applied to different scales and different applications. So for example, in this case, you can see here the specifications of the technologies. And then the third component that needs to be sized is this buffer tank. So we size this, and then we have to size the buffer tank. And again, here we use another factor that is called F buffer tank. So basically, this factor represents the fraction of this thermal energy storage capacity compared to the power that is exchanged under nominal conditions in this heat exchanger. In reality, there is some potential for optimization here, depending on the operating profile of the vessel. So what we want to do is to have this parameter as an optimization variable in the end of the day. And this is basically the F buffer tank factor that needs to be optimized. And this can be easily translated to an energy thermal capacity of the tank, and then we can calculate with it the mass of the oil inside the tank and also its volume. And you know that volume is critical for vessel engine applications because it directly tells us what will be the size needed for this tank. And then we come to the next point, that is the sizing of the latent thermal energy storage system. So this is this block here. And I remind you again that the purpose of this buffer tank is not to do thermal energy storage, but to do stabilization of the operating conditions. And here is where basically we have significant thermal energy storage. And again, here we use another factor. And this factor is called FLTS. And again, this factor shows us the scale, the energy storage capacity of this unit compared again to the heat duty of the waste heat recovery heat exchanger. So everything is normalized according to our approach. And after getting this factor that also needs to be optimized in the end of the day, it is possible to calculate the mass of the PCM, the phase change material that is needed for our system. And again, you understand that this is very important to evaluate the practical feasibility of this application because we have specific limitations with regard to the volume and also the mass of the thermal energy storage system. And finally, we have another parameter that needs to be sized, and this is the heat exchanger of this system. So inside this thermal energy storage system, we also have a heat exchanger, and this dictates the rate at which heat is supplied or removed from the thermal energy storage system. So this is another parameter that needs to be sized. And again, we follow a similar approach to this heat exchanger, to the heat exchanger that we followed previously. We define an input and outlet nominal temperature for the heat transfer fluid, and based on some overall heat transfer coefficients, it is possible to get to the area of this heat exchanger. So we have all these parameters that are dimensionless, and the goal of this dynamic modeling platform is to find out what the value should be to get the best, let's say, energy savings. So after defining everything, the size of the system, we get to the dynamic modeling methodology. So the goal here is to have a time series and then solve the energy balance of the system at each time step throughout the cruise of the vessel. So for the heat exchangers, we use the NTU method, the effectiveness NTU method, to calculate the heat that is transferred at each time step. And then we solve also the energy balance equation of the thermal energy storage tank, of the thermal energy storage system. And then, as I told you previously, we have these performance maps, and these are basically tables with or polynomial equations, which correlate the heat that is absorbed from the active ZHENIT technology at its time step with the temperature of the heat transfer fluid that is applied to it, the mass flow rate, and also the temperature of the seawater. So basically, with these performance maps, I come back to this point here. It is possible to calculate at each time step what is the heat that can be recovered from the technology, how much electricity is produced, how much cooling is produced, and this is useful for also getting the temperatures at each point of the diagram and carry out all the simulations. And yeah, one important aspect here to highlight, it is very complicated, so I will provide just a brief analysis, is the operating modes of the system. So as you understand, we have this thermal energy storage system and this, and what we can do many things at each time. So for example, what we implement is that we check the temperature at the top node of this buffer tank, and depending on the temperature level, we decide whether to either charge the thermal energy storage system, or to discharge, or to supply directly the active ZHENIT technology with thermal energy to produce some useful product. So this is I don't want to go into details about this, but if you want, I will be very happy to discuss it. And what we are doing in the project is we are developing this platform that I showed you in Transys software. So right now we have a fully developed Transys model for the ORC system and also for the isobaric expansion engine. And the plan is to proceed with the development of the model for the sorption desalination chiller and then integrate everything together. And you can see here some results, some simulation results that we have derived for the ORC operation. You can see, for example, here during the profile, the waste heat engine profile of the vessel for the cruise, of the cruise vessel, you can see that we can identify variations in the temperatures of the storage tank, in the state of charge of the thermal energy storage system, and we can also calculate at the end of the day what is most important: produced electricity and fuel economic and CO2 savings. So this is the presentation, and of course I am very happy to answer questions.
Thank you, Kostas, for your presentation. Okay, I can see that we have two questions, so I will bring everyone on screen and we can answer them. The first one is about the isobaric engine expansion engine, and they're asking us, can we assume the TRL of the technology is 7? What do you think the TRL will be after optimizing the feedback frequency?
Yes, answering the question, when we start this project, we consider like, I don't know, TRL3 or something like that, because it's like an experimental proof of the concept, no? Because it's something that is not, we don't have a clear idea of the concept. So due to that, this first step, we can include in this TRL3. When we validate the concept experimentally, and we consider like a validated technology, then we can consider TRL4, for example, but TRL7 is too much.
Okay.
For our point of view, yes.
Thank you very much, Joseba, for answering.
Yes.
The second question is about the ORC. What TRL we can currently assume for the technology?
Okay, if we see it as a standalone technology, I mean just an ORC, the TRL, we have commercial manufacturers providing ORC systems. The main innovation that we have in this project is the coupling of this technology with the ejector and also the vapor compression cycle that I showed you. The goal after fully automating the prototype is to have a TRL of about 5, because what we are going to do is that we will have some emulation of operating conditions in the laboratory, not on a vessel. So this will be approximately the end TRL.
Great, Kostas, thank you so much for your answer. Okay, I don't see any other questions at the moment, so I think we can wrap up the meeting. I thank you again, my speakers, and of course the attendees for this interesting webinar. And I remind you that the recording of the meeting will be available soon on our project website and as well on social medias. So stay updated to know when it is available, and you will also find all the presentations that our speaker just showed you today. So thank you again, and we'll see you at the next webinar for the ZHENIT project. Thank you very much. Bye, everyone.
Thank you. Bye.
Bye bye.
Thank you. Bye bye.
Thank you. Bye.